And let's try today. I'm trying today to talk about the classification a bit more, and just a few words about the MongoDB. If you have something to ask, please do so. So I have gone through the data analysis exercises until the at least week 3. And there are still some exercises to be evaluated. I haven't gone through these ones, for example, but I will during this week. I will analyze the rest of the exercises done so far. Um, and this week, wait, okay, the name is wrong. I have done something funny. It's the name. But before going to data analysis, just a few words about the data storage. I will do or publish the rest of the exercises at some point. Those are the old ones. Let's go to student role. So there are still a few more weeks to come here. But if you need, as I said before, if you need a MongoDB server where you can do these exercises, I have a running server now, which can be contacted with the, for example, with the Robo 3T. This is a free program, and I can make you user and password combinations here, so you can use the server to do the exercises if you want to, or you can use your own virtual servers, of course. So it is quite simple to use. If I wait, connect, edit connections. So this is the server, and then just put the, I give you the name of the database and username and password, and then you can log in and then you can make the exercises here, and you have also a command line shell here where you can write the different commands. For example, use pet. So you have to select all the text, and then there is the run, and you can see it changes to that directory, and so on. Then you can run all the commands needed in the exercises here, and you see the command results here. And you can also see the insights of these databases. For example, here I have the pets collection. I have inserted a few of the pets in the workbook. So for example, you can see the results here and so on. And of course, you can use the MongoDB command line here also. For example, the now this database there. It's like in my SQL, very similar this login. I don't know why it failed. Okay, it needs the password there. But just in case you are in trouble with your own servers, then I have a running system now. Any questions so far? Have you been able to do the MongoDB exercises? I think they were quite nice. If not, then let's talk about the classification problems a little more detail. The deadline is until October, but I will talk about this now, so you have time to understand, hopefully. So chapter 3, and in this chapter, the author describes a method to identify handwritten numbers. I'm not going through all the details, just the general lines of the theory here. And there are some things like classification algorithms, linear regression, decision trees, and random forests, which will be needed to understand some of the text. So here are links, what they mean. So decision tree is very simple thing in principle. So you make a choice, you have one possibilities, yes or no, and then you can have a more complicated decisions depending on the problem. It's like in programming languages, you have yes or no if statement. Either it's okay, Dimitri, that's nice. That the exercises were interesting. So decision trees, it's like an if statement. For example, here you have ones and zeros which have some features like color. They can be either blue or red, and they may have underline underneath. And in the decision tree, the first question can be, is it red? Yes or no? And in this case, all the blue ones will be classified in one group. Then there are nothing else left. All the blue numbers are zeros. But the red ones can be either ones or zeros. So the question is now, is the number underlined or not? Yes or no? Then you have three classes of numbers. Of course, this idea can be extended to more complicated things, like classifying the numbers, handwritten numbers here. So then what a random forest is. So we have, in random forest, we have large number of decision trees as an ensemble. And each individual tree in the random forest gives a prediction, class prediction. And it's like in the voting in democracy that class with the most votes becomes our model's prediction. And the fundamental concept between random forest is simple but powerful one. The wisdom of crowds. In data science speak, the reason that the random forest model works so well is that a large number of relatively uncorrelated models operating as a committee will outperform any of the individual constituent models. So if there's a low correlation between the models, then when you have a very large number of these randomized models, the large number of them will predict the result correctly. While some trees may be wrong, many other trees will be right. So as a group, the trees are able to move in the correct direction. So here are you see 5 random forests which predict either 0 or 1. So as a conclusion, 6 of these trees predict 1s and 3 predict 0s. So this whole ensemble gives a prediction of 1. So let's take another example. Very simple game. We have a uniformly distributed random number generator which produces a number from 1 to 0 or 1 to 100. And if the number this operator generate is greater than equal to 40, you win. And okay, I pay you some money. If it's below 40, I win and you pay me the same amount. And now I offer you the following choices. We can either play 100 times, betting 1 each time. We play 10 times, betting 10 each time, and play 1 time, betting 100 each time. So all these 3 games have the same expected value of 20. So in each case, I will win. Oh no, the player, or you will win 20, for example, $20. But if you run the simulations, for example, 10,000 times, you see the distributions are completely different, although the expectation value is the same. So more you play, the better result you get. It's the same idea with the random forest. So it's the law of large numbers, which is very known in the statistics. that when you repeat the experiment many times, the result will go as a normal distribution like this, smallest here, a Gaussian distribution. So if you play one time, there is, of course, there are 40 to 60 possibility only, two possibilities. Either will win. And if you play 10 times, you have the distribution like these bars here, and when you play 100 times. So in this case, you make money in 97% out of the game. And in 10 times, you make money in 63% of the simulations, and of course in this case 60%. So in random forest, each tree is like one play in a game. A gradient descent is another classification method, which is an optimization algorithm that tries to find a local minimum in a dataset. It must have a differentiable function, so it calculates the partial derivatives of all the variables and then tries to find a local minimum according to the direction of the gradient. So the gradient is a derivative in many dimensions. And in this case, the algorithm goes to the direction where the gradient is most negative. And that way it tries to find the local minimum of the function. Okay, that we don't have to go to the mathematics, but the idea is that when we, for example, start from x here in x0 and then calculate the gradient, it's always in the tangential direction to these blue lines. It points to this direction of the red arrow where we end up in point x1, then we calculate the gradient again here. It can be also numerically calculated, as you may know. The derivative in numerical form is just difference between successive points in a dataset. So in this way, the algorithm calculates a gradient which points to this local minimum, which this is the point where it's going. Another picture here. Okay, here you see quite easy polynomial function called Rosenbrock function. Of course, this is a polynomial function which is very easy to derivate analytically. And if you plot this function as a function on x1 and x2, you see the curves like this. And then when you calculate the gradient in different points, you see a curve like this. It goes to here, where is the local minimum of this curve, this particular curve. Here is another function. The gradient goes to this local minimum. And as you see, there are other minima here, also in here. So it can be somewhat random into which on these local minima it goes. Here's an analogy. It's like going down from a mountain in deep fog. You can just feel what's the direction of the downhill. It's like calculating the gradient, and that way you end up in maybe in some local minimum, where at some point it doesn't matter which direction you try to walk, it's always uphill. So then you are in the local minimum. The stochastic gradient descent is a randomized version of gradient descent. So in this method, you don't calculate the entire gradient in the entire dataset, but estimate it by taking some randomized subset of the data. And when you have high dimensional, so you have many parameters in your optimization problem, this reduces the computational burden. But I'm not going through this theory deeper than this. Just give you some idea about this, some of these classification methods. Then support vector machine is one of the classification methods used in supervised learning, as we do here. Maybe it can be seen in this picture. So in this method, you can, or this algorithm tries to find a line that separates two datasets. Most. So the distance between from the dataset, from each dataset to this line H3 is at the maximum. For example, here this H1 does not separate these two datasets at all. This H2 does separate the datasets, but only by a small margin. But there can be found one line that has the maximum margin to both of these datasets, and that's the idea of this algorithm. It has a fancy name, so support vector machine, but the idea is quite simple. Here's another picture. Without going into details more than this. But if we go now to the original problem of classifying these handwritten numbers, in this beginning of this text, the author describes how to classify one single number, namely number 5. And this example uses the MNIST image database, which is very famous and popular dataset. When you open the Jupyter Notebook, it runs this example through, so you don't have to care about where it is actually located. The link seems to be working, so it just fetches the dataset for you. So this MNIST dataset consists of 70,000 images, and each image has 784 features. And in practice, the images are 28 times 28 images, and is consisting of pixels, and each pixel has a gray level value from 0 to 255. So here is one of the images, and as it looks like 5, its label also tells us that this really is number 5. And you see the different gray levels. This label is a string, so this here the algorithm converts it to integer. And here are some of the images inside this MNIST dataset. Remember, there are 70,000 of those, so there's just a small part. But the idea is that we use the classification algorithm to classify the numbers from 0 to 9 and analyze how well these different algorithms work. As we have already discussed before, in these supervised learning tasks, we need a test set and a training set. And this MNIST database is already split into these training and test sets. So there are 60,000 training images and 10,000 test images, which can be split quite easily. And then here is described how to train a binary classifier. So there are only 2 possibilities. Either the number is 5 or it's not 5. So here the first classifier this text uses, or this example uses, is the stochastic gradient descent, which is suitable of handling large data sets efficiently, like I mentioned before. Okay, in this course, we don't have to understand every detail of the mathematics. We don't have enough time, or I think some of you and also me don't have enough mathematical skills to understand everything. Although I've got a PhD in physics, but I'm more from the experimental side, so my math skills are not that great. But it's for this course, it's enough that you understand the basic theory or basic idea behind different machine learning algorithms and how to use it. Use these Python scikit-learn tools in practice. Now here we in this text we are ready to detect images of number 5. And if the classifier guesses that this particular image represents a number 5, it gives true. Otherwise, it of course gives false. And then there are methods to validate the accuracy of our predictions or classification. And in this case, we get 93% accuracy. So how many correct predictions we get? And this, of course, looks very amazing. But let's remember what the original question was, whether it's 5 or not 5. So if you have 10 digits, you already have 90% of those numbers that are not 5. So in any case, you get, even if you just make a random guess, you are right in 90% of the cases, because 90% of those numbers are not 5. So in this case, if this algorithm gives you 93% accuracy, it's only 3% above this random level. So usually when we evaluate the performance of a classifier, we look at the so-called confusion matrix. So we count how many right classification we have and how true, well, right and wrong classified cases we have. So for example, in this 2x2 confusion matrix, you have the true negatives here and true positives here. So, and we have the true values in rows and predicted values in columns. In this case, first row of this matrix considers non-5 images. So 53,000 of them were correctly classified as being non-5s, so they are true negatives. So these 1,522 were wrongly classified as 5s, so they are false positives. And here, this 40,960 with 4,096 is the number of true positives. So this is the number of 5s in the dataset. So the handwritten number was 5, and this algorithm also identified it as 5. And this number, 1,325, is the number of false negatives. So this means that the number actually was 5, but the classification algorithm say that no, it's not 5. And false positive means that it's this classification algorithm says that this number is 5 when it's actually it's not. Okay, this can be quite confusing. I know myself. It's always I have been struggling with these concepts for many years. Years ago, I worked in a hospital as a physicist, and of course, these things come there also when you make a diagnosis. So there, it's very critical that you find as many true positives as possible. For example, in some cancer diagnosis. We didn't have any machine learning algorithms at that time. We had simpler methods to analyze the images, but we did some diagnosis from the, for example, from MRI images to recognize whether there is cancer or not. But anyway, this confusion matrix was used there also. The same principle. So there are a few things that we need to define. First is the precision, which is the ratio between the true positives divided by true positives plus false positives. Then another important thing is the recall, which is the true positives divided by true positives plus false negatives. And when you illustrate now the confusion matrix, you have the true negatives in the upper left corner, true positives in lower right corner, false positives in upper right corner, and false negatives in lower left corner. So for example, in this case, these 5s were correctly classified as 5. This number, which seems to be 6, was falsely classified as number 5. So this is false positive. These numbers evidently are not, none of them is number 5, so they are correctly classified as not 5. So they are true negatives. And these numbers are number 5, but they were falsely classified as not being 5. So they are false negatives. So you can then move this vertical line. If you move this vertical line, you can have different number for this precision and recall. For in this case, the example in this case, we have true positives is 4, and the sum of true and false positives is, number of true positives is 4, and false positives is 1. So in denominator we have number 4, and in here we have 3, so its precision is 3 out of 4. And then recall, we have again 3 true positives and 2 false negatives. So there are sum of these is 5 and true positives is 3. So recall is 3 out of 5. And now there are several ways to illustrate these precision and recall. They can't be both 100% at the same time. Usually when precision increases, recall decreases, and vice versa. So now this accuracy is not that shiny as it was before. When you calculate here, you calculate the using the same data set that here before. When you calculate the precision and recall, you have precision 73%, recall 76 about. These can be combined in one metric called an F score, F1 score. With when it's close to 1, the closer to 1 it is, the better. Or is it? Wait a minute. The larger it is, anyway. The larger it is, the better. I think it can't go above 1, if I remember correctly. Of course, it can. The extreme value is 100% or 1. So you can't have it both ways. Now, if you look at this picture, if you put the threshold in the middle, you see that now you have 6 numbers on the right side, where there are 5 of them are rightly predicted or classified as 5. Sorry, 4 of them are rightly classified as 5, and 1 is wrong. So precision here is 4 over 5, or 80%. And the recall, you have a total number of 1, 2, 3, 4, 5, 6 number of 5s. And 1, 2, 3, 4 of them were correctly classified. So the recall is 4 over 6, or 67%. Now I think, wait a minute, I put on the Teams chat. Why it doesn't go? Wait a minute, for some reason my Teams chat is missing. just continuing just in a few moments. Okay, let's continue. Now, if you move the threshold here, you see that the precision goes up. You have 3 5s rightly classified as 5. But now the recall has dropped into 50%. And if you put the threshold here, precision goes down, recall goes up. So they are always moving opposite directions. Okay, here are some coding details that I'm not going through. Just you can't set the threshold manually, but the program somehow magically determines it for you. But when you, okay, then let's take a look at this plot where you have the threshold for this image classification task. This number is the number of the images. Therefore, it's so large. Remember, the total number was 60,000 in this training set. So usually we want high precision, that we find as many true positives as possible. So here, if you want, you can't have it 100%. So you always classify everything right, because then, as you see, if you want this blue curve go to 1, then the recall is very, very bad. And another way around. So you have to make some reasonable compromise, for example, that you classify 90% of the cases correctly. And then you have recall about 0.4 something. And then the corresponding threshold is around, is it 6,000? It's explained in the text somewhere here. $8,000. So you decide to aim for 90% precision. You look up the first plot, and you need the threshold about 8,000. Then you see that for this 90% precision, you have recall about 0.44. Here is another way to illustrate the same thing. Now here we plot the recall versus precision. And here you see that when the precision drops to about 0.6, then the, wait, another way around. When the recall goes to about 0.9, then the precision starts to drop very rapidly here. So maybe you could, in this case, if you want to study what the optimum recall is, then it may be around 60, which gives about 80% precision. Here the blue dotted red line is the same as in here. So this is the same information plotted in two different ways. One more curve is the ROC, or Receiver Operating Characteristic curve, which is also very common. I remember this from my hospital days also. I didn't understand it then. Now I think I maybe I understand. So this ROC curve plots the true positive rate, another name for recall, against the false positive rate. So it looks like this. So this blue curve, the classification is the better, the more higher it goes. The closer this blue curve is to this upper left corner, the better classifier we have. So in ideal case, it goes just here and then it goes very close to this upper limit. So, but in general, you see here that when the true positive rate goes up, then the false positive rate goes also very high. It starts to increase. Here is another picture using here is the now the steepest stochastic gradient classifier has been replaced by the random forest classifier. You see here now this ROC curve goes very close to this upper left corner. So this is better classifier than this one. So what this means? So here the false positive rate remains very close to zero until here at this point where the true positive rate is already very high. It's very close to 1. Then it starts to increase very rapidly. Another parameter that can be determined from this ROC curve is the area under the curve. So area under this, for example, is dotted blue dotted line. And it can be from 0 or from half, 1/2 to 1, where this black line gives the area under the curve. Of course, it is 1/2. You have 1 times 1 divided by 2. So this area is 1/2, and the extreme case is that the area is exactly 1 times 1. So the closer this area under the curve is to 1, the better classifier we have. Then we can also have multi-class classifiers. So far we have only have the binary classifier, either the number is 5 or not 5. But naturally we can have a multi-class classifier that can classify all the 10 digits, 10 numbers at once or in one process. And one way to classify this system is make 10 classes and train 10 binary classifiers for each digit. So one classifier detects zeros, one classifier detects ones, and so on. And this is called one versus the rest, OVR, or one versus all strategy. Another is a pairwise classifier where you distinguish ones and zeros, ones and twos, and so on. So a pairwise classifier. And this is called one versus one classifier or one versus one strategy. Of course, this means in this problem this means that you have to train 45 binary classifiers. This scikit-learn algorithm program that we are using here is so smart that it detects automatically which is the suitable approach. So with a few lines of code, it trains this support vector machine classifier on the training set from 0 to 9. But I'm not going into details here. Let's see just the error analysis. When you have done the classification for all the 10 digits, here you see now the confusion matrix. It's now 10 times 10. So here in each row you have the true number, and in each column you have the predicted number. So this means that in the diagonal you see the true positives. So for example, in this case, it has predicted or classified the number 0. So the first column here shows that it finds 5,578 zeros and so on. So here it's just plotted in a image format. I don't think it's very informal. And these non-diagonal elements are, of course, they are those wrongly classified. digits. For example, here the true number, for example, in this row, the true number is 1, and in 6,410 cases, the classifier was able to say that, okay, this handwritten digit really is number 1. But in 35 cases, it confused 1 with handwritten number 2, and here with 3, and so on. And in almost 200 cases, it confuses numbers 1 and 8. So this is really informative matrix. You see all the false, true negatives also there, and true negatives, true positives, so on. In this case, you may notice that this number 8 has been poorly, badly classified, since there are there are large numbers here, so it has been confused quite a lot with other numbers. Somehow it has been very hard to classify correctly. Okay, I'm not going any further with this theory now. I hope it was somewhat helpful with the future exercises. Do you have any questions? Quite a lot of theoretical material today. If not, then we stop here. If you have any questions later, then please ask. I will stay at the Teams chat after this lecture if you have something. Or you can send me email directly.